As we continue on our hunt for the shortcuts of calculating derivatives, we might think about all the limit laws that we had for limits. One of them said, if you're taking the limit of the product of two functions, you could just take the limit of each function individually, then multiply them together. And if we think about that relationship, we might think that this statement at the top of the screen is true. Because see, a limit and a derivative are very similar. At this point, we have the limit definition of a derivative. So if we can do this for limits, can we do it for derivatives? And the answer is no, we cannot. I'm going to show you why in just a second, but let's appreciate the fact that here we have f times g, and then we're taking the derivative of that product. What I'm telling you is not equal to that would be if you took the derivative of each function separately and then multiplied them together. So that doesn't work. There is a shortcut that we're going to use, but unfortunately it's not as nice and neat as that one is. To find the shortcut that is correct, we're going to assume j is some generic function, which is made up of a product of two other functions, f times g. And then we'll use that general form of j to find j prime using our limit definition. First thing I'll do is replace my numerator. Instead of writing things in terms of j, let's write them in terms of f and g. So j with x plus h plugged into it is the same thing as f times g, with each of those having x plus h plugged into them. And then I'll subtract j of x, but instead of writing j of x, I'll write f of x times g of x. And then we'll copy over our denominator. Now our goal here is to manipulate this huge limit that we have written in yellow so that we can see a derivative of the function f, and so that we can see a derivative of the function g. So we're looking for these two expressions. And we see a lot of the things that we need in this large limit that we have written out in the center of the screen, but they're not really organized the way that they need to be. So we're going to do a little bit of mathematics manipulation here. And the first thing that we're going to do is add and subtract the term f of x times g of x plus h. So I'm adding it here first. I'm also going to subtract that exact same term. And the reason why we're adding and subtracting that exact same term is because if we do that, it's essentially like what we have written in blue is 0. So we're not changing the value of our limit. We're just being really sneaky about what we're doing. And I am adding that into my numerator. So this entire expression is over the denominator h. Now if we look closely, we can see that the terms we've added will group nicely with terms that we already have. For example, I can pair up this first yellow term and this last blue term. And what I mean by pair up is they both have a common factor of g with x plus h plugged into it. And then the other two terms in our numerator, I'm going to pair those ones up as well. And notice that they have a common factor. They both have the f of x as a factor. So I'm going to group these and write them all out so that it'll be easier to look at. Now that's not a whole lot better, but we can now see the common factors in the first two terms, so we can factor that out. And in factoring that out, we can see that we are starting to create that f prime definition that we're looking for. We see the f of x plus h minus f of x over h, and then we see that we're multiplying by g on the outside. We're going to have that same thing happen with the other two terms. Notice that these terms have f of x as the common factor, so that's what I'll factor out. And then I'm going to reverse the order here. We have a minus g of x and a plus g of x plus h. I'll write g of x plus h first, then minus g of x following. And because we do have those limit laws that allow us to separate sums, I'm going to write these as two separate limits where h is going to 0. Now we do have another limit law that would allow us to separate these products into other limits, so let's go ahead and do that as well. Now having it written like this, we can see that we have f prime showing up in this white box, and we have g prime showing up in this second white box. Now we do have two other things here. We have the limit of h going to 0 of g of x plus h. If we let h go to 0, that actually looks more like g of x, and that is multiplying to that f prime. And then in the second one over here, we have the limit as h goes to 0 of f of x. And there's not even an h in there for us to worry about. So as h turns into 0, that still looks like f of x, which is multiplying to the g prime. And this is what the true product rule says. That if you are trying to find the derivative of two functions that are multiplying together, like j, the derivative of that follows this pattern. You take the derivative of one of the two functions, multiply it to the other function. Notice that this g does not have a derivative notation on it. So that's the original g, but this is the derivative of f, and they're being multiplied together. And then we're going to add to that the derivative of g times f. So notice here, f is the original f function, but here g is the derivative. So the true product rule says that when you take the derivative of a product of two functions and you want to separate that, what you do is take the derivative of that first function, multiply it to the second function. Then add to that the original first function multiplied to the derivative of the second function. So we are taking the derivative of each function separately, but notice that there's some extra factors that are playing in here. Let's practice using this product rule. Sometimes you're asked to find a derivative at a particular value, and you're not even given the definition for the function. Instead, you're just given particular values. So even if we weren't asked to find j prime at 2, we know that j prime, the derivative for a function j that has a product of f and g, that would look like f prime times g plus f times g prime. So the derivative of the first function times the second function plus the first function times the derivative of the second function. So if we wanted to find j prime at 2, then we would need the derivative of f with 2 plugged in. We would need g with 2 plugged in. We would need f with 2 plugged in. And we would need g prime with 2 plugged in. And conveniently, those are exactly what we're given as part of the problem setup. So let's go ahead and start swapping things out. F prime at 2 is -4, so F prime at 2 right here, that would become -4. G at 2 is +1, so G at 2, that would become +1. So we have -4 times 1 to start with. Then we need F at 2, so F at 2 is equal to 3, so we'll replace F at 2 with 3, bring down our plus sign, multiplication, and then the last thing we need is G prime with 2 plugged in, which is 6, so we replace G prime with 2 plugged in to be 6. And then we can simplify using order of operations, so we'll multiply to get -4 plus 3 times 6, which is 18. And then we add those to finalize, so we get a +14 for our answer. So in this first example, we're not really calculating any derivatives, we're just using the product rule to take information that we have answers for and arrange it into the right format to calculate the derivative of the function j. In the second example, we are given the actual definition for j, and we want to use the product rule to calculate this derivative. Now, the first thing that I like to encourage you to do is create a roadmap. So j prime, that's the same thing as taking the derivative of the entire j function. And when we write it out like this, we can see that we have a product of a function of x and another function of x. So we're multiplying two small functions of x to create j, the larger function. Once we identify these, we can go through and calculate all of the things we need, kind of like in the last example, how we were given all of the things we need. Now we need to find them on our own. So we know we need f prime, which is just the derivative of that first factor, x squared plus 2. And we can use our shortcut rules here. The derivative of x squared is 2x. The derivative of 2 is 0. So f prime is simply 2x. We also need g prime as part of our product rule. G prime is just the derivative of 3x cubed minus 5. 3x cubed turns into 3 times 3x squared. And then the derivative of minus 5 is 0 because 5 is a constant. So g prime is simply 9x squared. Notice that we're using our shortcut rules here to calculate derivatives rather than using those limit definitions. And wow, that goes fast. So that's awesome. Now our last step is we know we're taking the derivative of this product, which according to the product rule would look like f prime times g plus f times g prime. Now we just found f prime and g prime. F prime is 2x. G prime is 9x squared. We know the definitions for f and g as well. Those came straight from the original definition for j. So we're just going to simply replace f prime, g prime, f, and g with their function notation. So f prime is 2x times g, which is 3x cubed minus 5, plus f, which is the x squared plus 2 factor, times g prime, which is 9x squared. And then we can distribute and try to combine like terms here. See if we can simplify our answer. Looks like we have a 6x to the fourth and a 9x to the fourth. Those are like terms, so we can combine them together. 18x squared and a minus 10x. Now, we use the product rule mainly because the directions for this exercise says to use the product rule. But it is true that we could have FOILed this out and then calculated the derivative term by term using those basic rules that we learned at the very beginning of this section. That's a great way to check your work, but make sure that when you're reading the directions for whatever assignment you're working on, if it says use the product rule, you need to use the product rule. Multiplying out the original j function and then taking the derivative term by term, that's not the same activity, so pay very close attention to detail there. Also, just for clarity, I realized that when I copied this example out of the book, I did not write the problem down exactly like it was in the book. So if you compare this to example 3.24 on page 254, you'll notice it's a little bit different, and I challenge you to see if you can find what the difference is.